Okay, we are now recording. Trying to share the screen here. Okay. Okay, so we're here. I'm actually done with 2.2, so I'm starting 2.3 today. So perhaps I'm kind of a day ahead. I might even sneak in some of 2.4 by tomorrow. Okay. Quiz tomorrow, and it'll be a quiz where I'll ask you for limits. I'll give you a graph, and might ask you for the limit from the left, limit from the right, two-sided limits, and a function value. Okay, so your answer might be a number, it might be DNE, does not exist, might be infinity, might be negative infinity, all that kind of stuff. It's not very long. In fact, tomorrow's quiz is so short, some of you might finish in just a few seconds, and I haven't even made the breakout rooms yet, so just hang in there, be patient. You'll finish in plenty of time, but it'll be so fast, you might get done real fast, but just bear with me. I'll set up the breakout rooms, just like other quizzes. I'll put you in groups of 3 or 4. You put down your first and last name, please. Everybody else's first and last name. If you don't do it, I might take off points. Okay. And then you check to make sure that you get it right, and you check to make sure that all your teammates get it right. And again, I will grade just one person. So I'll look at all of them, but I'll just grade one of them. So since you don't know who I'm grading, the only way to be sure is to make sure that everybody gets it right. Okay, so I'll do something like, one of these graphs like that, right? I might say, okay, what's the limit from the left? What's the limit from the right? What's the two-sided limit? What's the function value? Okay. So you might give me a number, DNE does not exist, or infinity or negative infinity, stuff like that. Okay, so that's tomorrow's quiz. All right, so let's get started with 2-3. I gave you an introduction yesterday, and now we'll do problems. So we have 3 to 31, odd, 41, 45, 47, 53. Okay, and then I'll show these to you again. Not sure if I showed this to you yesterday, but for those of you that don't plan on getting the book, page 102. Here we are. And some pictures there. Some more here. And there. And while I'm showing you this, I'll blab a little. We're not going to be making tables for the most part here. Okay, so when it says x approaches 16, like 27, or t approaches 0, we're not going to be plugging in. That is very, very tedious. Okay, there must be something better, and I'll show you the better. And so here, and how far do we have to go up to? Let's see, 53. So I do have to show you 53. And there's 53. Okay. All right, so we're ready. Okay, now, problem 3. So as I mentioned before, there's something called a direct substitution property, which says if you can plug it in, just do so. Limit as x approaches 3 of 5x cubed minus 3x squared plus x minus 6. Okay, just plug it in, no problem. 5 times 3 cubed minus 3 times 3 squared plus 3 minus 6. Grind it out, 105. Okay. Now, even though in this case, when you plug in 3, you get 105, that's not really what this is saying, right? What this is really saying is that if I plug in a number that's very, very, what? Close to 3, either on the left or on the right, I get a number that's very close to 105. Okay, that means I'm not plugging it in. But if I were to plug in 2.999, I'd probably get something very close to 105. And if I plug in 3.001, I get something very close to 105. Okay, so if you can plug in, just do so, which really makes it just an algebra 1 problem, right? So that's for number 3. Same thing for, I'm not sure about 5, whether you can see number 5. Yeah, I'm pretty sure for number 5, you can just plug it in. Number 7, you definitely just plug it in. Don't be scared by that cube root and all that stuff. Just plug it in, and it's very straightforward. Okay, so they're not really very challenging. So the challenging ones are the ones starting with 11. So if you look at 11, 13, 15, 17, you can't just plug in. And you can see why. X approaches 5. 5 minus 5 is 0. 5 minus 5 is 0. Negative 3, I'm pretty sure when you plug in negative 3, you get 0. I think that's the idea behind the problem. Yeah, H approaches 0. You can't do that, right? So what do we do in this case? Look at 19. Negative 2, not allowed. 21, H is 0, not allowed. 23, X is 3, not allowed. Okay? So certainly, you're not going to get a whole lot of problems like this. That's too easy. That's just algebra 1. Okay? So what happens in these cases? And it says evaluate the limit if it exists. In many cases, the limit exists even though the function does not exist right at that point. So for, let's say, number 11, I will declare the limit does exist, even though f of 5 is not defined. Okay? You cannot plug in 5, but in reality, we're not plugging in 5. We're plugging in a number that's very, very close to 5, like 4.99 on the left or 5.01 on the right. Those are defined. Do we approach any number? The answer is yes. So, oh, man, I don't feel like making a table. You don't have to. Quite often, it's just some algebra trick. So let's look at 11. Should be pretty straightforward. Okay, so limit as x approaches 5. Okay, factor out the top. X minus 5, x minus 1. That's very easy. You're all very good at factoring because you're in calculus. These guys cancel out. So limit as x approaches 5 of x minus 1. And now you can directly substitute, right? After you cancel this out. By the way, this is allowed if x is not equal to 5. X is definitely not equal to 5 by the rules of the game. X is near 5, but not equal to 5. So I'm allowed to make that cancellation. Okay, so now limit is x approaches 5 of x minus 1. Just plug in 5. 5 minus 1 is 4. Okay, so for almost all the rest of these, there's some algebra trick that you want to do. Okay. All right, so that's the basic idea. I'll show you some more. 17. Limit as h approaches 0 of negative 5 plus h squared minus 25 all over h. Okay, you cannot plug in directly, right? How come you can't plug in directly? You can't divide by 0. Okay? But I will declare that this limit probably exists because you're not really plugging in 0. You're plugging in numbers that are very close to 0. Get close to 0, 0.1, 0.01, 0.001. And on the other side, negative 0.1, negative 0.01, negative 0.001. Do we have to make a table? No. Do some algebra. Okay, square this. That's like a squared plus 2ab plus b squared, right? So negative 5 squared. Okay, then 2 times a times b is negative 10h plus h squared minus 25. 25 cancels out. So you have these two terms left on top. They have a common factor of h, right? Factor out the h parentheses negative 10 plus h divided by h, and now that h cancels out. Okay, this will be a very, very recurring theme. Okay, you try to get that h to cancel. Once we do something called derivatives, I know some of you have had calculus, you know what I mean by derivatives. Others of you have no idea what I'm talking about for derivatives. Don't worry, you'll find out soon enough. Okay, there's going to be an h in the bottom. How do I get the h to cancel? There has to be an h in the top to cancel. Almost always it's like that. Okay, so notice the 25 cancel out. Both of these guys have an h. So you factor out the h, cancel. Now I can plug in, right? So limit as h approaches 0 of negative 10 plus h. Plug into 0. Answer is negative 10. Okay, and notice there's no table here. It'd be very, very tedious, like some of the problems that you did at first, to plug in, you know, 0.1, 0.01, 0.001, negative 0.1, negative 0.01, and so on. And you'll see the numbers get close to negative 10. So if you look at the table, I'm guessing on one side you would see negative 9.999. The other side would be like negative 10.001 or something like that. Okay. Okay, there's some other trickier ones. Is if you have a fraction and a square root, it'd be like 21 and 23. So 21, radical 9 plus h minus 3 over h, and 23 has a weird looking fraction. So how do you do with those? Let me show you. There's a certain trick you have to do for 21. Cover this up for a moment. Limit as h approaches 0 of square root of 9 plus h minus 3 all over h. Okay? The original is in blue. Extra stuff that I wrote is in green and red and so on. Okay? Again, don't plug in. If you plug in, you're going to divide by 0. Okay? Yeah, some of you have noticed you often get a 0 on the top. But you don't have to get it. You actually don't have to have a 0 on top. But the main thing is you can't plug in directly. Okay, here's the trick. You've heard of rationalizing the denominator in algebra. In this case, we're going to rationalize the numerator. Okay? So you multiply by the conjugate of the numerator. The conjugate of radical 9 plus h minus 3 would be radical 9 plus h plus 3. Okay, so these two are called conjugates. Okay? If this was a plus, you would make this one a minus. If it's a minus, you would make it a plus. And let me raise it up. Okay, so again, the original was like this. Use my finger to cover it. The original was all in blue. Stuff that I put new is in different colors, like red or green. So again, you multiply by the conjugate of the numerator, which is radical 9 plus h plus 3. Top and bottom, of course. Whatever you do in the top, do in the bottom. Remember, when I put this extra factor here, you're really multiplying by 1. And when you multiply by 1, you don't change the value of the expression. Okay, that way, the numerator now looks like a minus b, a plus b, right? And from your algebra 1, what is a minus b times a plus b? That's a squared minus b squared. Right? And that's nice because what do you get when you square the square root? You just have 9 plus h. Minus 3 squared is 9. Okay? So the numerator ends up being 9 plus h minus 9. The denominator is h times radical 9 plus h plus 3. Don't multiply out the bottom, by the way. Just leave it alone. The 9s cancel out. So now in the numerator, I just have h. Guess what happens to that h? Cancels that h. Okay, so again, that 9 cancels that 9. You now have an h, and that h cancels this. So on top, you just have a 1. Okay, so that's the trick. Okay, so if you see something with square root, think of multiplying by the conjugate. We're rationalizing the numerator, right? Before in your algebra, you rationalized the denominator. Now you're rationalizing the numerator in this case. Okay, so now on top you have 1. The bottom you have radical 9 plus h plus 3. Now you can directly substitute. No problem. Okay, so limit h approaches 0. So put a 0 there. 1 over the square root of 9 plus 0 plus 3. That's 9. Square root of 9 is 3. So 1 over 3 plus 3, 1 over 6. Okay, and a quick word about notation and how you write it. Okay. We're supposed to teach you to write mathematically correct expressions also. So you're supposed to keep writing limit h approaches 0 until you finally substitute in. Okay. So I will take off points, perhaps, if you don't keep writing limit h approaches 0, limit h approaches 0. It properly belongs there. Okay. It's not the same thing as leaving it out. So limit h approaches 0, limit lim h approaches 0, lim h approaches 0. Then when you're ready to substitute in, then you plug in, then you don't write it anymore. Now, on the other extreme is sometimes students say, oh, he's going to take off points if I take off limit h approaches 0. So you keep writing limit h approaches 0 until the very end. No, your final answer should not say limit h approaches 0. So I'll take off for that too. So the last thing you write, okay, the last thing you write should not say limit, blah, blah, blah. Limit x approaches 5 or whatever. Okay, you keep writing limit x approaches 5, limit h approaches 0, up until the point that you substitute in. After you substitute in, don't write it anymore. Your final answer must not say limit h approaches 0. I will take off points if you don't. Okay, so you have to be able to write mathematically correct statements also. Okay, so you keep writing lim, lim, lim until you're ready to plug in. Your final answer, don't put the lim stuff. Okay. All right. So next one I'm going to show you is 23, which looks pretty bad. Okay, so here's the original. Limit as x approaches 3 of 1 over x minus 1 over 3 divided by x minus 3. Okay. Again, can I plug in 3? No, you're dividing by 0. That's frankly too easy. They're not going to give you that many problems like that. So suppose it's a limit as x approaches 2. This is too easy. It's just algebra 1, right? You just plug in and clean up the expression. Okay. But we're not allowed to plug in 3. We're not really plugging in 3, right? We are plugging numbers that are very, very close to 3. So how do I clean this up? Okay. Well, what's the common denominator here? 3x. Multiply top and bottom by 3x. 3x over 3x. What is 3x over 3x? 1, right? So again, I'm multiplying the expression by 1, which means I'm not changing its value. And then I distribute. So that times that is 3. That times that is minus x. Don't multiply at the bottom. Leave it as 3x times x minus 3. Notice I keep writing the limit, x approaches 3. And do you recall this? We had that in our first chapter. I even gave you something like that on the test, I believe, right? 3 minus x divided by x minus 3 is negative 1, you might recall. Right? It's got to be minuses. So watch out. Time out. If it said 3 plus x divided by x plus 3, 3 plus x and x plus 3 are equal. So that fraction will be 1. And maybe I'll put off to the side here. Sidebar. 3 plus x over x plus 3 is equal to 1. They are equal. 3 minus x divided by x minus 3 is negative 1. Okay. So now I have this. And please notice, lim, 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 keep writing lim. Okay. If you don't write it, I can take off points for that. Okay. So this is now negative 1 over 3x. Now I can substitute because I'm not dividing by 0 or anything. So put a 0 right, a 3 right there. So negative 1 over 3 times 3. Final answer is negative 1/9. So again, you should not write limit as x approaches 3 of negative 1/9 in your final answer. Final answer is just negative 1/9. And there we go. I'll raise it up again for focusing. Maybe I'll go back to these if you want to look at the video later. Because you might be doing this fast, but you can always pause the video and go forward or backward at your leisure. All this stuff here, hopefully. Okay. I do see something in the chat. Let me see if I can get it. All right. I think we're good. Okay. Okay. Next one I'm going to show you is 31. 31. Limit as h approaches 0 of x plus h cubed minus x cubed all over h. This time our expression has two variables, x and h. And that's not actually going to be so unusual. We're going to see that more and more. Okay, behind the scenes, I'm chuckling a little bit at this, and Prasanna is, because Prasanna knows what I'm talking about. You'll see a lot of stuff like this very shortly when we do derivatives. And some of you who have background in calculus, you've seen stuff like that. Okay, but here's our first instance where it's not just one variable, right? There's an x and an h. So like this one has only t, right? This one has only x, only t, or whatever. This one has x and h. So my final answer isn't going to have any h, because h is going to approach 0. But my final answer is going to have x in it. Okay, so let's see what it is. So limit as h approaches 0 of x plus h cubed minus x cubed all over h. So in my final answer, there's going to be x. There won't be any h. So what is x plus h cubed? Okay, so I have to take a little time out for that and run through that bit of algebra. So x plus h cubed, well, you can think of it as x plus h squared times another x plus h. Okay, and we know the shortcut for x plus h squared, x squared plus 2xh plus h squared. Okay, so this is x plus h squared. Then you multiply it by another x plus h, right? And so you should know the way it goes. You take this and multiply it by these two. Then you take this, multiply it by these two. Then take this, multiply it by these two. Right, so x squared times both of them would be x cubed plus x squared h. I know, I'll just point to them. That's x cubed, x squared h. These two. Now I do that one. That times that is 2x squared h. There it is. 2xh squared. Okay, and then the last one, multiply these two, xh squared, and that times that is h cubed. Okay. It's just algebra, and you're all very good at algebra. Okay, combine like terms. These two combine, x squared h plus 2x squared h is 3x squared h. 2xh squared plus xh squared is 3xh squared. Okay, so I've expanded x plus h cubed is all this stuff. X cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, so that's all this stuff. Okay, side note, there's another way to do this with something called Pascal's triangle. You may have heard of that before. I'll show that to you maybe when we get a fourth power. If we end up doing an x plus h to the fourth, I might be willing to show you that. Okay, if you know what I'm talking about with Pascal's triangle, great. If you don't worry about it too much now. I'll just show you what it kind of looks like. Pascal's triangle looks like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. Sometimes called Pascal's triangle. I'll set this off here. Okay, seen this before? The outsides are all ones. Then for any inside number, you add the two numbers that are right above it. So right above the 2 is 1 and 1. Right above the 3 are 1 plus 2. 2 plus 1 is 3. 3 plus 3 is 6. 1 plus 3 is 4, and so on. You just keep going down. This leads to binomial coefficients. So in other words, 1, 3, 3, 1 match to 1, 3, 3, 1 over here. So anyway. So if we get to a fourth degree binomial, then I might talk a little bit more about it. If you don't understand anything I said here, I'll know how to multiply that out. Okay, so getting back to this. So this stuff I'm replacing with this now, right? X plus h cubed is this mess, minus x cubed all over h. X cubed cancels out, x cubed minus x cubed. Okay, and similar theme. That term, and that term all have a common factor of h. So factor out the h paren, 3x squared plus 3xh plus h squared all over h. And you're starting to develop a pattern. H cancels out. That's the whole idea. You want that dividing by 0 to be eliminated. So now I have limit as h approaches 0. Again, please notice, lim h approaches 0, lim h. You keep writing it until you're ready to plug in. So now I have 3x squared plus 3xh plus h squared. Now I plug in h equals 0. So if I put 0 there, that's gone. Put 0 there, that's gone. That's an error that says 0. That's an error that says 0. So now that I substituted in, don't write lim anymore. So 3x squared plus nothing, 3x squared. Okay. Okay, then I want to show you 45. Limit as x approaches 0 from the left of 1 over x minus 1 over absolute value of x. Okay, again, you cannot substitute right away. Okay, absolute value of x. Okay, quick timeout way over here. The absolute value of x is the same as x if x is greater than or equal to 0. It's negative x, that's a negative there. Negative x if x is less than 0. You can think of that as a definition of absolute value function, right? We know it's V-shaped. So if you look at the graph, that's y equals x. That's y equals negative x, right? So absolute value of x is the same as x if x is greater than or equal to 0, negative x if x is less than 0. So back to here, x approaches 0 only from the left. That means I'm only considering this case, correct? I'm only plugging in negative 0.1, negative 0.01, negative 0.001, negative 0.0001, and so on. So I can replace absolute value of x with negative x because I'm only plugging in negative numbers. Okay? So I can change this problem to 1 over x minus 1 over negative x. Okay. So ignore the red temporarily. It's 1 over x minus 1 over negative x, because absolute value of x is negative x if x is less than 0. And then what I do here, I have a double negative. Okay, it's going to be negative, 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 plus. So that gives me 2 over x. So limit as x approaches 0 from the left of 2 over x. Okay. I hope you can get some proficiency in not making a table. You could make a table. I don't think you need to. You should know intuitively that if you divide by a very small number, you get a very big number. Okay. So 2 divided by negative 0.0001 is a very big negative number, negative infinity. Okay. So you should have already heard before the concept that if you divide by a very small number, you get a very big number. Okay. So negative infinity. Okay. Okay, then let's see, I want to give you a little bit on the greatest integer function. What time is it? Okay. Okay, so I alluded quickly to the greatest integer function in 53. Greatest integer function, we round down any fraction or decimal part to the nearest integer. You always go down. So if you already have an integer, reminder, what's integers? 0, plus or minus 1, plus or minus 2, plus or minus 3, right? No decimals, no fractions. Okay. The greatest integer function on an integer is the number itself. So greatest integer function, it's hard to write. It's like this bracket, bracket. The greatest integer function of 3 is 3. Greatest integer function of negative 4 is negative 4. Okay. But once you have any decimal or fractional part, you always go down. So greatest integer function of 4.99 is not 5, it's 4. You do not round off, you round down. Greatest integer function of pi is like 3.14, 3. Greatest integer function of negative pi, okay, your gut reaction might be to say negative 3, but it isn't. Remember, you're going down. So from negative 3.14, go down to the nearest integer would be negative 4. Okay. And we've looked at the graph before, right? So let's take a look at the graph. I alluded to it the other day. Greatest integer function. Okay. Page 101. If you want to put that graph on your cheat sheet, you may. It's a step function. Okay, it looks like you're walking up some steps. So closed circle on the left side, open circle on the right side. Okay. Because the greatest integer function of 0 is 0, closed circle, 1, 1, 2, 2, 3, 3, and so on, right? And the function value is still 0 if I have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.99, 0.9999. Then once I get to 1, it jumps up to 1. And then I move 1.1, 1.2, 1.5, 1.9, 1.999. It stays 1, right? And then it jumps up to 2. That's what it looks like. Okay, so for 53, a little bit with this. Okay, 53. Limit as x approaches negative 2 from the right. Limit as x approaches negative 2, period. Okay, so sorry, I can't write it at the same time. We approach negative 2 coming from the right. We approach negative 2. Here we are. Coming from the right side. Negative 2. Okay. So the answer to 53AI is negative 2. 53AII, two-sided limit. Okay, look carefully. There's no plus or minus next to the negative 2. So two-sided limit doesn't exist at any integer, right? Because you're jumping at every integer. They don't show it, but there's another piece down here. So 52A II should be DNE. Okay, so this one over here, sorry, I can't. That one right there. 53. 53AI was -2. 53AII, hard to see all these parts, does not exist. How about 3? Limit as x approaches -2.4, double-sided. That's going to be okay. -2.4, well, they don't show you the graph, but it doesn't matter if I'm a little bit to the left or a little bit to the right of -2.4. If I'm at -2.39 or -2.41, in either case, you're going to go to -3. So that limit does exist. Okay, so 53A III, the third one, the answer is -3. Okay, how do you do B? If n is an integer, evaluate x approaches n from the left, x approaches n from the right. I thought I would just analyze it by seeing what happens when x approaches 1 on either side. Okay, now I could show you the picture, but I don't think I need to. X approaches 1 from the left, 0.9, 0.99, 0.999, okay? All of those numbers, when I plug in, 0.9, 0.99, 0.999, 0.9999, they would all go to 0, right? Again, you don't round up or round off. You have to go down, so that would be 0. If I come on the other side, 1.1, plug in 1.1, 1.01, 1.01, 1.0001, those would all give me 1. Okay, so you can see there's a 1, 0, 1 stays 1. So that means in general, it looks like if I'm coming from the left, you subtract 1. So limit as x approaches n from the left of the greatest integer function is n minus 1. Greatest integer function as x approaches n from the right is the same as the n itself. Okay, so this one is n minus 1. This one is n. And if you just look at an example, 1 from the left is 0. 1 from the right is 1. So it looks like so. And then for part C, 53C, for what values of a does the limit as x approaches a of the greatest integer function exist? The hint was number 3. And again, look at the graph. Now, the two-sided limit exists for all the in-between points, but the two-sided limit does not exist right at the integers. So we will use this language. The limit as x approaches a of the greatest integer function exists for which a? The two-sided limit exists for all non-integers. If you do not have an integer, the two-sided limit exists. Okay, so two-sided limit does not exist at 0, 1, 2, 3, -1, -2, negative. That's where the graph jumps. Okay, you have a jump at those values. Okay. So that's what's happening there. Okay, and I think that's it. Let me check the chat real quickly for something. Somebody put something in the chat. Okay, so why isn't it -2? I have to think about what you mean. I think you're talking about, I believe the question concerns this one, where to go? It was the one with -2.4, right? I think that's what you mean. I can't find it anymore. Yeah, this one. Okay, so for the greatest integer function, x approaches -2.4. So how about -2.39? If you plug in, what would you get? You would go down. Going down would be -3, not -2. And if you go -2.41, you would still go down to -3. And a part of it going down is because it's negative, right? If you're at -2, if you go down, it isn't -1. If you're going down, it's -3, right? So if I move a little bit to the left or a little bit to the right of -2.4, it doesn't matter. If I say -2.41, it's going to go down to -3. If I go -2.39, it's still going to be -3. So any of the in-between points, we can find a two-sided limit. That's not going to be true right at the end points, right at the integers, right? Because you do not have a two-sided limit right at the integers. Okay, so for instance, the limit as x approaches 0 from the left is -1. So the limit as x approaches 0 from the right is 0. Okay. All right. The limit of -2 was the limit of -2 would not exist. F of -2 is -2. The two-sided limit at -2 does not exist. Because if I pick a number like -2.01, that drops down to -3. But if I pick -1.99, that becomes -2. So the two-sided limit would not exist. Okay. All right. That's that. How much time is left? Not that much. Okay. I'm going to do an introduction to the next section, but the next section is really weird. Okay. It's on the precise definition of a limit. Okay. Right now, I'm just going to give you some symbols for the most part. Then I'll give you something to do. And that's about it. Okay. .4. Okay, this funny symbol is delta, Greek letter delta, small change in x. Okay. Now you say, well, I thought the triangle was delta. Yes, the triangle is an uppercase delta. This is lowercase. Greek has upper and lowercase just like we have upper and lowercase, right? That's delta. It's meant as a small change in x. The funny looking E is epsilon, small change in y. Okay, so here's a little delta, here's an epsilon. I guess it's like alphabetical order, x, y, delta, epsilon, right? So tiny change in x, delta, tiny change in y, epsilon. Okay, here's a number line. How far is it from a to x? Well, just subtract x minus a, right? Like if this is 3 and this is 10, you would just go, oh yeah, 10 minus 3 is 7, right? Suppose I have it reversed. Suppose a is bigger. So it looks like this. A is here, x is here. Then you would say a minus x. Right? It depends on which one's bigger. I've already shown you this. But anyway, suppose now you just say on a number line, the distance between x and a, and I don't even tell you, or maybe you don't know, which is the larger. Okay. So what's the distance between x and a? Well, if it's like this, it's x minus a. If it's like this, it's a minus x. I just have to make sure it's positive. We have a way of making things positive.
Absolute value.
Absolute value. Right. So how do I say the distance between x and a in general? Absolute value of x minus a. You could also put a minus x, but I want you to put x minus a. The formulas that we have involve x and a. Okay, so the distance between x and a is absolute value of x minus a. Okay. Similarly, the distance between f of x and L stands for limit later. Okay. Absolute value of f of x minus L. Now, suppose I want the distance between x and a to be smaller than some number delta. Distance between x and a, there it is. Argument over here. Okay. I want it to be smaller than delta, so there it is. Absolute value of x minus a is less than delta. You're going to be able to write all this on your cheat sheet if you want. I'm just introducing it right now. Distance between x and a is smaller than delta, but it's not 0. Greater than 0. That's because when I do the limit stuff, I don't want x to equal a. So I have to write this now. 0 less than absolute value of x minus a less than delta. This is just an introduction. Your head might be spinning right now. That's okay. Don't worry about it for now. But we're going to end up with a lot of this stuff. Okay. Distance between f of x and L, this, is less than epsilon. We have this stuff. Absolute value of f of x minus L is less than epsilon. Okay, and that's all I wanted to show you. You say, I have no idea what you're talking about. That's okay. We'll talk more about it tomorrow. I'm going to stop and give you that, but I'm going to show this to you in case you want to look on this on the video. And of course, it's in the book. So I'll show what I had there. Okay, so distance between a and x, that's x minus a minus x. So I don't know which is the bigger and the smaller. So absolute value, right? Okay, so distance between f of x and L, absolute value of f of x minus L. Distance between x and a is less than delta, but not 0. And distance between f of x and L is less than epsilon. Okay, so that's as much as I'll tell you right now. Okay, last few minutes. Have you do one of these. So if you don't have the book, take out your cell phone. And I just want you to do one of these. Hopefully it's not too bad. Where did it go? Okay, I want you to do problem number 12. Okay, right here. 12, limit as x approaches -3 of x squared plus 3x over x squared minus x minus 12. Don't plug in right away. You won't be able to. Okay. Do a little bit of simple algebra. Factor the top, factor the bottom, cancel, and then you can plug in. Okay, type in your answer as a private chat, then you can leave. Okay, so again, just number 12. Okay, I'm going to hold it just a little longer. So if you don't have the book, if you have the book, just go to 12. If you don't have the book, take a picture or do a screenshot. Next couple of seconds. Limit as x approaches -3, x squared plus 3x over x squared minus x minus 12. You're not going to be able to plug in because the bottom will be 0. Factor the top, factor the bottom, cancel, and then you can plug in hopefully. Okay, your answer should just be a real number. Just give me the number. Okay, I'm going to put this down because the book is heavy. All right, and that'll do it for today, folks. I'll stop the share. I'll stop recording also.